All right, so today we're looking at chapter 7. So remember that chapter 6 was about that keyword right there, analysis of sequential systems, the flip-flop circuits that we've been working with. And now we're going to be working on the design. And I always like the way the Dr. All says the word design, especially when he's teaching that design course. And that's a key part of what our engineering physics program has in it, the ability to design mechanical or electrical systems to solve big problems. To refresh what we did in chapter 6, we went from analyzing, there's the word analysis there, analyzing a flip-flop circuit. And from that, those connected wires, we got a next state equation with those asterisks on there. And then from that, we built a next state table, which is right over here with ones and zeros. And then we built a state diagram. And the point of all of this was to understand what that circuit is doing. Because if you look at that circuit, you can't tell what its function is. But so in order to communicate with a human, you have to kind of put it in this form. And we think more in terms of flow charts, like what happens first, what is the if-then condition to go from one state to another. As you can imagine, in chapter 7, the arrows are basically going to be opposite, or at least we're going to flip this diagram upside down. But there's a few little differences here. We do start with a state diagram. You could start with a state, you could start with a state diagram, but you could also start with a state table. So it's kind of optional whether you have this, this thing right here, that state diagram. It's kind of optional when you get into chapter 7. It's helpful for our brains to understand what the circuit is doing, so we're going to do it. But you can see that in order to get to the circuit, it's not entirely necessary. If you have a state diagram, you can create a state table from there. And then what you do is you add columns that give you the values of, let's say, J and K. If you're going to use J and K flip-flops to solve the circuit, it could be Ds if you're using D flip-flops, or RS or Ts. So it depends on what kind of flip-flop you want to use, what columns you would put here. On the test and on the homework, I tell you, use a JK flip-flop, or use a trigger or toggle flip-flop, or use a delay flip-flop. So the problem will often tell you what you're confined to use. In fact, the first homework set, the first homework problem in the back of chapter 7 says solve this problem using all 4 of them, which is really time consuming. So we're just going to use one pair of flip-flops, JK. After you get this, there's another intermediate step in which you use a Carnell map to get the next state equations. That's the step right here. And then finally, you're able to design a circuit that performs this task that's up there. All right, so you can basically see that we're going like this, and we're going like this, which is basically upside down. I guess I should have turned it upside down. I mean, there's some similarities, like you got flip-flop at the beginning, flip-flop at the end, state table in here, but there's a little bit of differences, but it's somewhat similar. All right, so what we're gonna do is now go over and see how you begin this chapter 7 process. We're gonna start with a state table. We're gonna add flip-flop columns to that state table, write down the next state equations, and then we're gonna build the circuit, hopefully in Multisim Live. And I'm looking forward to this lab prep this afternoon, because I think we're gonna give you access to virtual machines. So you'll be able to log in through a web browser to machines on campus at SFA to run the actual version of Multisim for lab this week. Instead of that Multisim Live version, you'll have all the advanced features if we work this out. And so far, it seems to be working out pretty well. All right, so let's move over to our homework for today. And I'm going to do like I normally do, and that is do one of the homework problems with you, which is problem, let's see, 1B. Where did it go here? Is this the screen I need to be looking at? I think that's it. All right, so I'm going to minimize that. Here we are. And let's see. So let's see. There's lab. Here's the homework. And I think I've already got it pulled up over here. Homework 9, chapter 7. All right. So in the textbook, if you look at page 483, you see this problem right here, and it tells you to make a state diagram. It says to use an RS flip-flop, D flip-flop, T flip-flop, and JK flip-flop. We're only going to use one, and that's the JK. We're going to then write or build Carnell maps to figure out what the inputs are to the JK JK flip-flops. And then we're going to do a circuit sketch, hopefully in multisim. Any questions so far? Okay, this state table right here is right out of the textbook. And I do want to show you that it looks a little bit different. What page is it on? I guess I had it up there. Question while I'm looking. Any questions so far? Okay. You will see, I don't know if this will be visible when I hold it up to the camera or not.
Can you just tell us the page number?
The page number is 483, right here on the screen.
All right. Oh, there it is. Thank you.
Yep. And I'm gonna put my camera on it right here. Hopefully, you'll notice that part A right there, notice that it only has 3 rows. But on the screen over here, you can see that I have 4. So 3 rows here and 4 rows there. The reason that is because some problems you don't need to have 4 states or 8 states or 16 or 32. Sometimes problems, such as a 3-story building, you only need 3 states because you have the 3 elevator states there. And that's actually the problem you're going to be solving in lab on Wednesday is the elevator problem. So what I did was I added this row and basically saying you don't care about those because the problem doesn't really allow it to go to that state. You look in these other values up here, the circuit never gets to 1, 0. So that state is not allowed to get there. That's normally why there's a clear button or a clear input on the JK flip-flop so you can make them 0 so that they don't accidentally go into a state that's not permitted. All right, so this is the problem. And so what we're gonna do is start the Mealy model diagram. I'm gonna start it for you and let you finish it. I feel like y'all are getting really good at making state diagrams. So I'll do a couple of wirings on here and then everybody will be able to copy what we're about to do and then finish it up and paste it into this space right here at the bottom. So here is our typical template that we use. This is actually 1B. Wait, this should be 1A, right? Yeah, look at that. That's the wrong one. All right, so let me see if I can correct that because that's not right. It should, because you notice there's no X's in here. I think I put the wrong link in there. So let me fix that. Probably can go back over here to find the proper link. We need to be looking for 1A, which is this one right here. And that is still wrong, isn't it? Okay, well, it says it up there, but nonetheless, what I can do is change that to an A, and then we'll just delete this and put the right thing in there for everybody. All right, so coming back over here, let's make sure that that goes to that site. All right, it did. And so then I'm just going to take this table right here and paste it in there for everybody. I'm not sure how the wrong table got in there, but we fixed it nonetheless. There's a little bit of formatting issues right here, so let me clean up that.
Dr. Bruton, where can we find this again?
All right, so what you want to do to find this homework set is you want to go to Course Tools, Dropbox.
Is it homework 9?
Yes.
Okay, it's not available yet.
Oh, let me make that visible to you. Sorry about that. Good point. Make visible to users. All right, there we go.
Okay, thank you.
I'm glad you pointed that out. Otherwise, nobody would be able to do anything. All right, so this link does appear to work now as far as getting to problem 1A, homework 9, and we got the X's in there. So let's do a couple of these, and I'm going to close out these other windows just to keep things clean a little bit. We'll get back to National Instruments in a minute with Multisim Live, but for now we'll do this. And so you can see that what you do with this first one, something's not happening right. Look at that. What is this here? I don't know what that square was. Okay, anyway, I've removed that square. Let's take this, and you know what we're doing right here. Go right there, and we're gonna go over here. What do I label this along the way? We're just gonna do 2 of these, and I'm gonna let you do the rest on your own. So instead of XZ, anybody want to type in the chat what I do or just say out loud?
0, 0.
0, 0. And that's because x was equal to 0, and as you can see over here, z is also equal to 0 as well. Let's do one more. What state do we go if x is equal to, what state do we go to if x is equal to 1?
Back to 0, 0.
Back to itself. Okay, so for those, I really like the way that this Google tool works in getting this back to there. And then what do we label the arrow for this melee circuit?
1, 1.
1, 1. Very good. All right, I will let you do the rest of those. And of course, what you can do is do a screenshot using your snippet tool and just copy that right there. And then you paste it right into this spot right here. In fact, you can delete this right here and just put your state diagram right there. All right, any questions about that? I can finish that one up. There's no ones in the circles. Below there's no horizontal lines because this is a melee model in which the value of z is along the arrows rather than in the circuit. All right, and so everybody can use this template, but I don't think you can edit it, right? You can only view it. So just go ahead and do the thing we normally do, make a copy, and you can kind of finish it up from there. Let's move on to the next step, which is step II here, and that's to make columns for JK. So you can see that everything over here is the same as what I had before, and everything is over here, same as I had before, but I'm entering these new, excuse me, these new columns that will help us identify what are the inputs into this block that we call a JK flip-flop. Let's see if I can kind of pull one up here. So if I go over here to create a circuit, I might actually have one that has a JK flip-flop already. I go into, let's see, go to my circuits, and there's the one we're going to be working with today. Open circuit, there's my JK flip-flop. There's input for J, input for K, output for Q, and Q prime. Looks like they put a tilde on there instead. That's all right. And then we got the clock coming in here that determines how fast it's making the decisions. So we're trying to determine what input goes here and what input goes over here. We have an X here and a Z output over there. And we'll get to that a little bit later. All right, so I'm gonna close that one and just work on this table. All right, so watch very carefully because it requires a couple of careful steps there. And then you'll see it, it'll just become easy all of a sudden. I highlighted two numbers here in red because what we're identifying is the case that if A is equal to 0 and X is equal to 0, then A becomes 1 in the next clock cycle. If you're going to use a JK flip-flop to perform that operation, to get it to go from 0 to 1 if X is equal to 0, then if you're going to use a JK flip-flop to do that, then you use this state diagram for a JK flip-flop. Here's how it goes. If we're trying to go from A being 0 to 1, I look down here and I put my arrow here on 0. That's the value of A, and I want it to become 1. And there's two ways that I can get it to flip over to that from 0 to 1. There's two ways that I can do it. I can let J be 1 and K be 0, or J be 1 and K be 1 as well. Either one of those for a JK flip-flop will get us from 0 to 1 if we're changing A like that. For that reason, what I can do here is put 1 and then X. Now, why did I do that? Does anybody grasp why I put 1X there? For the value of JA and KA if X is equal to 0.
Because it doesn't matter.
It doesn't matter about the value of K, that is correct. It matters about the value of J, which is basically saying set. That's why it's over here like this. And the 1, 1 basically means toggle, so that's why you see it down here as well. All right. It's a little bit challenging to explain this, but hopefully y'all be able to get this. So let's do another one. Make sure we kind of understand this. And let's just focus on A again. So I'm going to paint it red just so I can let everybody in the room know which letter, A, which flip-flop I'm talking about. So I have two flip-flops. One's called flip-flop A and the other one's called flip-flop B. All right, here's the basically the output of A there. All right, so 0, 0. Can anybody tell me if what I would do? What kind of value of J and K, JA and KA would be if I'm going 0 and I need to have it stay 0? What should I type in right there?
0x.
0x. So I need to stay right there. Going down to the next one, can't we just put don't cares for both of those? If we don't care where we land, we can actually just put don't cares across the whole thing here. Because we don't really care about this. We're not even allowing this two flip-flop state to exist. We only want to have 3 circles, and it's going between those 3. Oh, that's right. I forgot about that. Let's come back to this just for a moment. State 2, we should not allow. So what should I delete over here? This one, right?
Yeah.
So you can now just move these around, and now you just have a triangle, and you don't have to have a square there. So you can't really have an odd number of states. All right, what about this one?
X1.
Okay, so basically it's saying reset. K is basically kind of acting like a reset. And then the 1, 1 means toggle. Anyway, you got it, X and 1. X1, not X and 1, but X1. And that's the value of JA and KA for X equals 0. How do I get this one right here? Where do I look? I need to look at the value of A again, but now I got to look at the case where X is equal to 1. See there, X equals 1 right there? X equals 1 right here. I need to be looking at that right there. So I'm going to paint this one orange just to say, we're working on this column now. We're comparing this one right here, still orange, and I think somebody got it figured out. What was that, Jordan?
0x.
0x, right?
0x, and that's because 0 staying at 0, 0 staying at 0 again is 0x. Then down here, we go 1 to 1, from 1 to 1. I'm going to take the colors off of here now, so now we can go a little bit faster with this. It's 1, and A is going to stay 1 in the next cycle. So over here, X0, y'all are saying, good. And we keep going. All right. Now we're going to be focusing on B. So it's basically looking at this, and this, and that, and only the right-hand side. Now, what we're doing is we're looking at the B flip-flop, but it's still a JK flip-flop, so we can still use this diagram right here. But what's inside of here is the value of B instead, and this is JB and KB over here, like you see right there. Okay, so here we have B. It's 0 going to 1. What goes there?
1x. 1x.
And then over here is go 1 going to 1, or staying at 1.
X0.
X0, right?
Oh, right. That basically means stay right there. X0 for a JK flip-flop means stay right there. Now we're looking at 1, stays a 1. It's the same thing, right? X0. And we're almost done. So now we're going to focus on 0, stay in 0 over here.
0x.
And 1, 0.
X1.
And finally we go 1 and 1.
0x.
So it's 1, staying a 1. So it needs to stay right here. So X.
Sorry, X0.
X0, right? So it's basically all you needed to do right there. We got to figure out how do you use that. Looks like some kind of bookkeeping or game exercise right there. How can you use that to actually get to the point where you have a circuit that solves this problem, that keeps the circuit flowing in that particular series of states? And the answer is Carnot map. So what you do is you make a Carnot map for JA, KA, JB, and K. This should really say KB right there. Okay. So JA, KA, JB, KB. Okay, got it. So what we do is we look at just the value of JA right there. And we got to translate that into the Carnot map. Now notice it says X equals 0 right there, and this is X equals 0 in this column. Now I wonder if I need to probably temporarily move this so we get them closer to each other. So let me do this. I'm going to exit out right there, and I'm going to put it at the top. And you can certainly do that on your copy as well. So that way you can get these, together on the screen at the same time. So here we go. JA is this one right here, 10XX. What goes in the next column?
0, 0, XX.
All right, so we got to look at JA, which is right here for X equals 1. That's that column right there. And we got to do it in the right order. Remember, we're doing a reverse down here. So 0, 0, XX. So you have to go like this, 0, 0. And then you got to go down to the bottom. I'm doing that not because it's necessary, because we don't want to forget about it. All right. Then we go to KA.
Wait, Dr. Bruton, your Carnot maps aren't flipped. It goes from 0, 1 to 1, 0 to 1, 1.
Thank you. Let me correct that then. That's very good. All right, so I need to put a 1 right there and a 0 right there. I said it, but I didn't actually display it, did I? That's good. And so for the second homework problem, we should correct that as well.
It was a test. You passed.
That's right. Got it. All right. Now, going on to KA 00. Wait. Well, they need to be right here, right? XXX1. So this is wrong, correct?
Yes, that should be XX1X.
Right. So it's XXX. Okay. XX. X1. So you got to flip those back over. Same thing for KA. So XXX0. All right, then going on to JB. By the way, the reason JK flip-flops are preferable sometimes is you get a lot of don't cares, so that these equations turn out to be really easy, as we'll find out when I give you all the pen in a minute and let you do the K maps. All right, so we're going to do like a 1, an X, and an X, and an X for that right there. And then we're going to go 0. And you'll do the same thing for part B. By the way, this is the same steps, X, and X, and X. And you can see those equations look really easy. That's the power of the JK flip-flop, I feel like. I hope I did that right. All right, now we're going to go X, 0. And then I think we go X, 0. And then over here, X, 1.
Is it not 0XXX?
Okay, so.
Oh, no, sorry. I was looking at the wrong thing.
Okay.
I got it now.
Okay, I hope that's right. Okay, so 0, dun, 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 dun. Okay. And then this one is 0, correct?
Mm-hmm.
All right, let's see, just as a test of this new security measure, can anybody request control? Or like, no, annotate, I guess is what we want to do. Can you try to annotate and like do some circles on the screen? Anybody or everybody? Okay, so that's not correct though. So circle um, the group there. Okay, hi, good. That's very good. I wonder if maybe I can do it too here. All right, so I'm going to do this one. And what I'm asking for, okay, it says Tony requested remote control. I don't know if you want to do remote control, but let's try anyway.
Okay, I don't know what to do.
I think what you can do is annotate. Can y'all tell me where that's at? But wait, that's me. Wait, let me turn that off. I can't get my mouse back. There we go. Okay, let's see. Clear all drawings there. All right. So try view and annotate, and I'm going to do one over here as well.
Oh, okay.
Be great if you could draw. Oh, you can draw rectangles, can't you? So right here and right there. And there you go. And this one is wraparound. So this is one where you would have to kind of, yeah, this one you'd have to go, you know, you can't really do it with a rectangle there and there. All right, so what? Let's turn off all the annotation there, or at least get back to my mouse. What equation do I write right here?
X naught B naught.
And for KA?
X naught.
That's why I like that, because it's kind of simple.
A naught.
Right. And so the next thing to do, okay, is to clear the screen. So clear all drawings. The next thing to do is to use this to build the circuit. All right, so what we're going to do is go over to Multisim Live to do that. And so I'm going to go ahead and open that window up right over here. So one of the things that I noticed is that unless you get a full paid version of this, you can't find any flip-flops up in here. So that's why we want to go to these virtual machines. And Dr. Ochoa is going to show us that in lab prep on Wednesday. And it's going to give you all the components. However, I kind of found a hack to do this. I went over to GoTo and public circuits, and I noticed that some people with paid accounts had public circuits out there that had flip-flops on them. Searching.
You can save your own version as it and just use that flip flop.
Yeah, so what I did was I said, oh, this one's got some flip-flops on there, and I clicked it, and I go, I wonder if I can just make a copy of this for myself. I sure could. And so then I saved a copy. So then I made something for you all. If you go back to the search right here and use the phrase two JK flip-flops, and you'll see that in the homework. It says, go to the 9-square waffle. Is that what y'all call it, by the way? Let's see. Let me get back to this over here.
I just call it the dots.
The dots, okay. I'm you know, the 3 horizontal bars, I call it the hamburger, but I guess this one is like the 9 squares or the navigation menu, I guess. And you go over here to go to, you go to public circuits like this, and then you can look for, I wonder if you could just look for Dan Bruton. I wonder if that works. I mean, because I made the circuit public so that anybody in the world could get it. And I basically made a note also, oh, it found all my circuits there, good. So basically made a note out there that told the company that made Multisim, was like, please leave this out here while we're in quarantine for the note on this circuit. All right, so anyway, we're gonna open up the circuit, and that's what y'all can do. You can use my template as a starting point for building your own. All right, so then I wonder what I have to do to kind of get this so y'all can see both things. I think I might have to show my entire screen in order to make that happen. So let me go back to a new share, and let's go for screen number 2 and share. and then come over like this, and then have the homework over here. All right, so there's the equations. And where did multisim go? Da, 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 da. There. Nope. Close enough. All right. So the first thing I need to have is an input of some kind, X, that I can toggle around. You see that right there. And this is really, I wonder if it'll let me, label it instead of Q and Q prime. I wonder if it'll let me label it A. Perhaps not, but at least what I can do is label the whole thing flip-flop A for this one right here. This over here is going to be flip-flop B. Okay, this one I'm check. Y'all can see my whole screen, right?
Yes.
Okay. All right, so there's that. And then what we need to do is have some kind of, toggle for our input. I think where we found that was down here, a constant that we put right here. And then the value of this is going to be X. And this is what we're going to toggle back and forth as the clock is moving through. It's cycles from 0 to 5, 0 to 5 over and over. Here's our input. All right, based on these 4 equations, what kind of logic gate do I need to pull out of our toolbox and put onto the screen?
And
We need an AND. What else?
A not
not.
inverter.
All right, so we need a not inverter. Okay, so I'll get that right here. All right, so let's do the easy ones first. What do I do right there? What does that mean?
Go straight into K.
Which one?
That one, the A.
The A. All right, so we come out of the KA and we got to go right over to there. All right, one done. What about this one? That's the B and it's the J. So I have to go over here and right there. There's that reset that I was telling you about. We're not going to wire these up right here, but the set basically turns Q equal to 1 and the reset turns it to 0. That's in case you want to clear out all the states and just have it starting home like 0, 0. So that way, when you power up the circuit, it just doesn't land in a random state. It starts, say, on the first floor of an elevator. All right, 2 down. And so now we got the AND gate right here. Do you want to do some De Morgan stuff right here? Guess we could. What would De Morgan say about this equation right here?
XOR B.
XOR B, right?
Correct. Close. Yes. So that's basically a NOR gate. So let me grab one of those. A NOR. And I just need a 2-input version. That's a weird, wait, that's not it.
That's a XOR. Yeah.
That says, okay, got it. Oh, it's XOR. Oh, there it is. Okay. Understood. All right, so what we need to feed into that is X. And we could, initially connect it all up and then later clean up the traces, especially when you want to make a printed circuit board with this on it. You would kind of drag and drop and let the wires fall where they may until it looks clean. And now we're going to go, let's see, we need to have B. So where is that at? How do I figure out what goes here? Where's B at?
Is it the Q, the output Q?
There you go. See, that's the thing. I really wanted to label this B because that's the way it does in the textbook, but I don't think it lets you do that in Multisim Live. So we're gonna have to rely on the gate itself, or not the gate, but the flip-flop itself being called the B flip, the B version of the JK flip-flop, and this is the A version of that. All right, and the output goes to where?
J.
Just like that. And notice that the wires cross, and that means that there's no electrical connection unless you have this little dot that looks like that. So it's okay when that happens. I can't really see a way to clean that up other than maybe to, you know, switch the inputs. So we could, you know, try to do that instead. If I get my hand on that one, what I can do on this one is try to get my hand on that one, delete it, and maybe, you know, go to, you know, there instead. And then there, so it's X and B, slightly cleaner without any wires crossing, but we still have some crossing going on up in there. It's pretty hard to get rid of that. We can try to come down like that, but still you get a lot of wires crossing. We'll leave it like that for now. We've done 3 out of 4. Go into KB, which is this guy right here. We have those 2 inputs handled. We have one more input to go. This is where we need the AND gate. So we'll go ahead and feed that one in right there. And what we're going to do is take the value of X, and maybe we can move the clock closer to our circuit so that we can feed X value in just like that. And the last one, it looks like we're going to have A prime. And here's the cool thing about that one. You don't need another gate because it's right here. That's A prime right there. All right. I forgot one thing though, and that is we need some kind of LED, right? Why do we need an LED? Let's grab one of those, put it out here. The other way we can do it is Dr. Ochoa might say is use this voltage indicator. So either one is going to be acceptable. Why do I need this one? What should I label this? What's not really shown here, but we've really talked about it up here.
Z.
Z, right? So we have to put a value for Z over here. That's our output. Okay. Now, I guess I forgot to put a Carnell map down here for Z, but I wonder if we can mentally figure out what it is. I don't know. I just forgot to do it. So let's see where we can handle that. I wonder if I can copy just this portion of the Carnell map, put it down here, kind of like that. And then I need to write an equation for Z. So I'm going to take it like that, take that and copy it down here. And this is going to be my equation for Z. Z. And we don't know what it is yet, but we know it's not this right here. So we'll have to scroll back up here and do 0, 1, x, 1. 0, 1, x, and 1. Then we come up here, 1, 0, x, 0. Can anybody tell me what the equation of that would be? Looks like it's going to have 2 terms, right?
X naught B or X B naught.
Does anybody know what that is? What does that simplify to? You'd have to look on the inside cover of your textbook, and it's actually one of the, down at the bottom, it's one of the SFA equations. It turns out to be an exclusive OR. However, I don't really know how to do the circle right there. So it would be X or B, but how do I put a circle around this? Do I do it like this? Is that close enough? Right, so this basically simplifies. Instead of having 5 gates that I have to tie up in there, I mean, I have to have 2 AND gates, 1 OR gate, maybe, well, I already have the NOT gate and I have an output NOT. Anyway, I can replace several gates with just 1 exclusive OR gate. I think it's a pretty clever way of making an XOR when you don't really know how to do the circle around it in, say, Microsoft Word or Google Docs. Now we can grab the XOR. So that was complete accident when I did it before. And this is going to be the output for Z right there to there. How much time we got? 3 minutes, perfectly timed. And go right here like that. And we have the output of B, which is right there. And boy, did that make it a lot simpler just by recognizing that there's this SFA theorem. You don't have to do that on a test. If you end up doing that and putting the circuit for that up there, that'll be perfectly fine. But you can try to use these simplification methods from the inside cover of your textbook to make your life easier. I guess what you can do then is export it using the waffle. And it's down here. Or you could use the snippet tool, whichever you prefer. I just typed in SNIP under window, go like this right here. And then I noticed that I lost my thing, so I'll just try again. I lost my field of view, so I need to pull it back over like that. Make sure I have X and Z in there. Take that, and then I paste it right here. And then my work is done for problem 1A. So there's that step. I hoped we get to the point where either we're simulating these circuits in Multisim Live, or I get a chance to build these and then show it to you. Because what can happen is it's got a clock on that thing just ticking away for that DG1 right there. And then I can have it go at 1 hertz. And then what I could do is actually watch what I do with X, and I would see the outputs of A and B follow this pattern right here. So I could actually control whether it's going to stay right there and get stuck in that state, or if I want it to go there, then I pull X down. It's kind of hard to describe, but basically once you turn this power, excuse me, power to the circuit on, you can actually monitor how it goes through the states and control how it goes through the states as well. All right, that means my time is up. What happened there? What did I do on that part? Did it break or something?
I think it's just,
Huh. Yeah, it does kind of seem a little bit off like that. I'm not sure why. It does still seem like it is connected. All right, we won't worry about that because we're going to try to use multisim on the virtual machine. I'm going to stop the recording right here, show you something else, see if you have any other questions, and then we will wrap it up.